Good morning, ladies and gentlemen. Welcome to this video on looking at how integration and kinematics combine. So we've looked already at this from a differentiation point of view, and we know that if we differentiate displacement function, we get velocity, and differentiate velocity, we get acceleration. But now we have the ability to integrate, we can effectively go backwards. So to go from acceleration to velocity and velocity to displacement, we integrate. So we can do this chain in both directions. And there's a couple of tricks towards doing this in integration. Alright, so if we integrate the velocity function, we get displacement. Or, if velocity is purely positive, meaning there's no changes in direction, or purely negative, meaning no changes in direction, and if we integrate it between two times, t1 and t2, we get the area under a velocity curve, which is equal to the distance travelled. And note, this is only true if there are no changes in direction. If there are changes in direction, what we can say is that the change of displacement is equal to the definite integral of the velocity function between two time periods. That won't give us the distance travelled, it will give us how far it's displaced from its original position. And note that we don't even need to know its original position for us to be able to find this out. If we don't know the original position, we can still find out how far it's moved from it. We just don't know where exactly it is. I'll explain that more in a sec with the example. So in general, the integral of the velocity function is the displacement function. Alright, so let's look at how we can calculate total distance travelled. And we've done this already in one set using differentiation, but now let's look at integration. So, first of all, we need to be given, ideally, the velocity function. And then we need to draw a sign diagram for the velocity function to check if there's any changes in direction. Because when there's a change of sign in the velocity function, there's a change of sign, change of direction. Then we determine s of t by integrating and including a constant of integration. Find displacement of time 1, displacement of time 2, and also displacement of any time it changes direction. Draw a motion diagram, helpful for visualizing it, but not necessarily always necessary. Then determine the total distance traveled from that motion diagram. Alright, so let's look at an example. First of all, it asks us to write the formula for s of t. So formula for s of t looks like this. We want to integrate v of t dt. And if we're integrating v of t dt, because it's a nice simple polynomial, that works out quite nicely for us. Plus c. Right? That there is s of t. Now note, because we don't know c, we don't actually know the starting position, we just know the starting position or displacement in terms of t and c. Now we're asked to find the total distance travelled for the first 3 seconds of motion. So for total distance travelled, we first of all need to look at when v of t is equal to 0. So we're looking for a sign diagram to start with. V of t equals to 0 is the velocity function equals 0. 0 equals t squared take t take 2. Now, going back to your 10 quadratics, you're thinking, well, that's a quadratic. I'm looking for a sum and a product. This then multiplies to t take 2t plus 1. Took me a while there. Therefore, our solutions are t equals 2 and minus 1, and therefore our sign diagram for vt is going to be minus 1, 2, and in here it will be positive, negative. Positive, the good news for us is we're not really bothered about what happens with negative time. So we're looking for really only what happens with t equals to 0 and that way. What happens in the other direction doesn't so much concern us. So we can see here that there's really only one change of direction, and that's at time equals 2. So, to find the distance travelled, we need to look at the distance travelled between 0 and 2 seconds, and we integrate vt between 0 and 2 dt, and we add that to the integral of 2 to 3 vt dt. Now, if we pause for a second to think about what the graph of this velocity function looks like, the graph of the velocity function will look like something like this, because that's the other half of this, not necessarily peaking down there, having a trough down there, but it's going to cross at minus 1 and cross at 2. And this portion here, we're finding this area, and then we're looking for time equals 3. This portion, we'll be finding that area there. And we know from our work with integration this one will likely come out as negative. The other way we can avoid it coming out as negative is to switch these two around. Go from 2 to 0. So I'm not hugely fussed which way you do it. Switching that round from 2 to 0 will make the result come out as positive. Or if you leave it from 0 to 2 and get a negative result and think that's weird because you found an area and it's negative and it's a bit unpleasant, just remember to make it positive because you're looking for an area under the x-axis. So I'm going to go from 0 to 2, well aware that that's going to come out to be negative, but I'll make it positive in the end. Alright, now we know the integrand already, or the integrated function is a third t cubed minus a half t squared minus 2t plus c, and we're looking at that between 0 and 2, and then the same again between 2 and 3, and that doesn't take a switch because it's going to come out positive because it's above the x-axis. And then, unfortunately, this turns into rather a slog, but if you do it systematically, it's not too bad. 1 on 3, 2 cubed minus 1 on 2, 2 squared, minus 2 to the 2 plus c. Take 1 on 3, 0 cubed, minus 1 on 2, 0 squared. Take 2 lots of 0, rather. 2 lots of 0 plus c. Now, why'd I even bother doing the second one? Because clearly all those zeros are going to drop out to 0. The reason I did that is basically to show because it's a definite integral, that and a cancel, because this negative here will combine with that one there. Alright, and from memory, that entire thing will come to 10 or negative 10 on 3, or just 10 on 3. And then we add that to this one here, which you guys can do, and it will all come out to 5 1/6. Alright. That is the distance travelled, 5 1/6. 2c, find the particle's displacement from its starting position. So displacement from the starting position is the integral from 0 to 3 over the first 3 seconds of vt dt. So note there, that will give us this negative portion and that positive portion, and it's not clear from my graph because I've drawn it terribly which is bigger. It will end up some distance to the left or right of the origin, but it won't have travelled. It won't be a distance further than 5 1/6. It'll be less than that because we know we've done a change of direction. So what we would do here is we would do a third t cubed minus a half t squared, etc., minus a half t squared minus 2t plus c of between 0 and 3. And that works out, once you sub it in, to 1.5, meaning positive 1.5 meters to the right. So what's happening is we are moving, and in our position of movement, we've changed direction by that amount of time. Or that amount of distance, rather. Alright. Now, all of that is done without actually knowing where the initial position is, because RST had this plus C on the end, which meant that we couldn't get the initial position. So heading down here, we can find, well, what happens if our initial position is given, and how does that affect what we do? So this sentence here is incredibly important. That's called the initial conditions. Initially stationary implies that V of O equals O. And initially at the origin implies that S of O is O. So the velocity at time 0 is nothing. The velocity, the displacement at time 0 is nothing as well. And note that those two won't always be 0, 0. Sometimes the initial conditions will be, it starts 1 meter to the right and moving 3 meters to the left. So VO will be -3 and SO will be +1. Sometimes they'll give you conditions at certain times. So 2 seconds in, the velocity is 3 to the right. So 2 seconds in, the velocity is 3 to the right would look like V2 equals 3. And why is this important? Well, this is important because it lets us find the velocity and the displacement functions exactly instead of just in terms of c. Alright, in this case here, we're asked to find the velocity function given an acceleration function. So what we do is we want to integrate the acceleration function. And to integrate the acceleration function, we could write it as 2 bracket t plus 1 to the -3 dt. And if we're going to integrate that, well, this t plus 1 has come from a minus 2. When differentiated, the minus 2 would come out the front, so normally we'd deal with it with a half. So then we'll have 2 from there times the minus a half to deal with that minus 2 coming out. The minus half looks like that, which is just then added to c, and it'll equal minus 1 lot of t plus 1 to the minus 2 plus c. And that is our Vt. However, we've still got this plus c here, and that's where our initial conditions come in handy. So we're told that VO equals O, meaning O equals minus 1 lot of O plus 1 to the minus 2 plus c. Now, fortunately for us, that works out quite nicely. O equals 0 plus 1 is 1, 1 to the minus 2 is still 1, minus 1 lots of 1 is just minus 1 plus c, therefore c is equal to 1. Alright, then we are asked to find in B, s of t. So s of t is the integral of Vt. And we're going to integrate the function we found above, which is minus 1 lot of t plus 1 to the minus 2 plus 1 dt. Note that plus 1 is the c from here. And to properly answer the question above, we probably should have written this entire thing there as a full answer. But short on time, so moving on. So then to integrate this, well, this here has come from a t plus 1 to the minus 1, and that 2 will come out, so there that just has to be a half. And, no I lie, that doesn't have to be anything. It'll come from minus 1, minus 1 drops out the front, which is what we wanted up there, goes to minus 2, and then this plus 1 comes from a plus t, and then we've got the plus c on the end, and that is our displacement function. And we're also told the initial conditions. The initial conditions are 0 when time is 0. Alright, once again, this is 1 plus nothing plus c. C is equal to minus 1. So our displacement function is t plus 1 to the minus 1 plus t minus 1. That's our c there. Alright, so those first two are done. Then it says describe the motion at time equals 2 seconds. What we need here is A2, V2, and S2. And then in describe implies a sentence answer. I'm not going to go through it, but you need to sub in 2 to our acceleration, our velocity, and our displacement, and then describe that. So this came out as, it doesn't, but if it came out as 7, you would say it's moving 7 meters per second squared to the right. S of 2, let's say that's minus 4, that would be minus 4 meters to the left, or 4 meters to the left of the origin. It doesn't really make sense to write minus 4 meters to the left, but 4 meters to the left of the origin makes some sense. So basically, when they ask for initial condition or describe the motion at a certain time, then you sub it into all 3 and give a little interpretation for each of the 3. Alright, thank you very much.